We're now going to look at some examples where we're going to use the substitution method, but it's not so obvious. And by that, what I mean is, if we're looking to use the substitution method, and we see, like, for example, there's underneath this radical, there's kind of an inside function of x plus 1, but you don't have the outside function hanging on the outside. In fact, this is a linear term, and on the outside we have a linear term. And that's kind of a problem. So if this were x squared plus 1 underneath the radical, and then you had an x outside the radical hanging around, you'd be in good shape. You could use the substitution method because you'd have the derivative up to a constant multiple hanging on the outside. So in all the questions we're going to do here, we're not going to have that. We're not going to see the derivative hanging around on the outside of the function. But we're going to see that we can still use substitution. And there's going to be all kinds of little tricks here that are really kind of nice. What I'm going to do is for this example, I'm going to use the x plus 1. Okay? And when I do that, then my du is just equal to, the derivative of that is 1 dx. So in other words, my du is just equal to dx. Okay, so I could just substitute those in for one another. Now, what I'm going to do here is I'm going to put u in for this, but then I need to get rid of the x up here. So I'm going to take that u is equal to x plus 1, and I'm going to solve this for x. And I do that by bringing the 1 to the other side. And so I get a u minus 1 here. So x is equal to u minus 1. So what I can do is I can make the following substitution. In for x, I'm going to do u minus 1. And then in for x plus 1, I'm going to do u. And then for dx, I can do du. And you get that. And so now this is going to be something we can differentiate. So I could rewrite this as like u minus 1, u to the negative 1/2 du. And now I can distribute the negative 1/2 over. And then I get like u to the 3/2 minus u. Oh, sorry. I get u to the 1/2, positive 1/2, minus u to the negative 1/2 du. And now what I can do is I can integrate those. So that, I'll just do it over here. So this would be u to the 3/2 over 3/2 minus u to the 1/2 over 1/2 plus c. And now in this final step, I'm going to put the u back in here, and then I'll also invert and multiply the denominators. And there we go. We have our antiderivative. This is the integral. So the idea here is you can still do substitutions. You just got to make sure that after you do your substitutions, your final integral is in terms of it's with respect to du, and everything is in terms of u. Okay, so I can't just substitute this u here and have x over the square root of u du. I mean, you could do that, but then you can't integrate because this whole thing needs to be in terms. If you're going to take the derivative with, if you're going to take the integral with respect to u, then you want all of this in terms of u, and you can get it here. You just have to solve this over here. U equals x plus 1. Solve that for x, and then plug it in. And then after doing all my substitutions, I get something that I'm able to integrate. I can't integrate this, but I can integrate that, as you can see. So it's really nice. So the substitution method is kind of coming into its own. It's technique in and of itself that's not used just to undo the chain rule, but it can be used in a lot of different ways. So here's another example. So this is something I could integrate. We got x times x minus 1 to the 25th power. I could integrate this by actually expanding this thing out, but that would be a huge thing with a bunch of terms. Imagine foiling x minus 1 together 25 times, right? And so that's unreasonable. Now, I couldn't do a normal u substitution. If this were x squared minus 1 to the 25th and you had the x outside, again, you could do it, no problem, but they're both x's, okay? So I'm going to use very similar technique to what I used before. I'm going to let u be x minus 1, okay? And then my du is just equal to dx, and then I can solve for x, and that's just u plus 1, like that. And now I can plug everything in and convert this into an integral with respect to u. So the x here is u plus 1, and then in for x minus 1, I'm going to put in u, so this would be u to the 25th, and then we have a du. dx can go in for du. Just like that. And so now you can see I can distribute that over, and we get something much easier to integrate. X to the 26 plus, I'm sorry, u to the 26 plus u to the 25th du. And so now this would be u to the 27th over 27 plus u to the 26 over 26. Oh, sorry, I don't need this. Plus c. And so now I can plug the x minus 1 in for u, and maybe I'll put these coefficients out front. Nice. And this is just a lot easier to integrate then. We avoided having to expand all that out by kind of switching these around, and then we could distribute the u over and then plug things back in at the end. So very nice techniques here. It's kind of a nice tool. So let's look at some more examples. Now here is one where we kind of have reverse of what we need in order to normally use the substitution method. If this were squared and that were x, we could use substitution method like we normally do, but it's not. It's the reverse, right? But I'm going to let u be the 2x minus 1, or 2x minus 10 anyway, like that. And then my du would equal 2 dx, so I could do the substitution there. Except I'm going to bring the 1/2. I'm going to switch the dx out here for 1/2 du is equal to dx. So I'm going to place this in for the dx, and now I'm going to in for this. I'm going to put u, but then this I need to solve this thing here for x. So what I'm going to do here, I got u equals 2x minus 10. So I got 2x is equal to u plus 10, so that's moving 10 to the other side. Dividing both sides by 2, I get that x is equal to u over 2 plus 5. Or I think it's going to be easier in a moment because I'm going to have to FOIL this out, making this 1/2 u plus 5. Okay, so now here's my substitutions. In for x, I'm going to put this, but I'm going to be squaring that. So 1/2 u plus 5 squared. And then in for this, I'm going to put u, so this is square root of u. And then in for dx, I'm going to put 1/2 du. So now I got this whole integral with respect to u. Now if I FOIL this out, then I can distribute the u to the 1/2 over. Okay, so maybe what I'm going to do here is I'm going to pull this 1/2 out all of the way, and then I'm going to rewrite this 1/2 u plus 5. This is just going to help me FOIL this, and then write this as u to the 1/2 du. And now I need to FOIL this. So this is going to be 1/4 u squared, and then this is 5/2 plus 5/2, and 5/2 plus 5/2 is 10/2, which is 5. So this will be plus 5u, and then I got plus 25. This is a u here. And then I got a u to the 1/2. All of this is with respect to u. So now I'm going to distribute u to the 1/2 over. So this is going to be 1/4. This is like, this would be 2/2. So this would be, I'm sorry, 4/2 plus 1/2 is 5/2. And then I got plus 5u, and this would be 3/2. This would be plus u, or 25 u to the 1/2 du. Okay, so now I got a 1/2 out front, and now I can integrate each of these pieces. So this would be 1/4 u to the 7/2, so I'm adding 2/2 each time, and then I have a 7/2 on bottom, plus 5u to the 5/2, 5/2 on bottom, plus 25, this would be u to the 3/2, 3/2 on bottom, plus c. Okay, so now what I'm going to do is I'm going to multiply the 1/2 through and invert. I'm going to try to invert and multiply. I'm pushing it for me. So I'll do 1/8, and then I'll invert this and do 2/7 u to the 7/2 plus, and this would be 5/2 2/5 u to the 5/2 plus, and then this would be 25/2 2/3 u to the 3/2 plus c. So what I did is I inverted each of these and distributed the 1/2 through. So now I can multiply, and then I'm going to substitute the original 2x minus 10 in. So this would be 256 2x minus 10 to the 7/2, and this would be plus, this just goes away, and I got 2x minus 10 to the 5/2, and then this these cancel out, and I get plus 25/3, and this would be 2x minus 10 to the 3/2, and plus c. So you can see that oftentimes antiderivatives can be big, long, messy formulas, okay? But there you go. That's how you can use the substitution method then to solve something like that. Okay, so now I have let's see, I have two more examples here, and these are real. Probably these are not at all obvious, because the other ones have a certain feel where you're solving and resubstituting things in like this, and then I'm solving it around, and I'm doing all these substitutions. Well, this is going to be different, and you have to just play around with these, and I don't want this video to be super long, so I'll show you kind of what maybe my thought process is. I mean, I've been doing substitution for a long time, but one thing that I realize is you have this x to the 11th on the bottom, and what I realize here is I can break off. So this would be like, I'm going to do x to the 3rd. So you have this, and then break off an x to the 8th. So in other words, if you multiply numerator and denominator, you'd get that. But the reason for doing this is that I can split up the radical, and this would be 1 over x to the 4th here. So in other words, I would get something like this. And then I'd have 1 over x to the 4th dx. And what I'm thinking is, if I had like a 1 over x cubed, the derivative of that would be 1 over x to the 4th. So in other words, that's what I do have. So if I break this up over the numerator, break the numerator up over the common denominator, I get 1 over 2x cubed. And then I have a 1 x to the 4th dx. So in other words, now if I let my u equal 1 minus 2x cubed, then I do get the derivative on the outside. By splitting off some of the factors of this bottom, I get something that is the derivative of the remaining portion. Okay? Really pretty tricky. So let's see how this works in. So du, so this is like, I could say negative 2, and this would be like bringing down a negative 3x to the negative 4th. Then I'll say du dx, and then I can solve this for du. This would be like 6x to the 4th dx. So I'm just taking the derivative of that, moving the dx to the other side, and now I'm going to move the 1/6 down here. 1/6 du is equal to 1 over x to the 4th dx. And of course the reason for doing that is because now I got this and this, I can substitute 1/6 du in for that. And so this whole thing, putting u in for this, I get the square root of u, and then I can put in 1/6 du. So it becomes that, and then I can pull out the 1/6, and I just got u to the 1/2 du. So this is 1/6 u to the 3/2 over 3/2 plus c. And then inverting this becomes 2/18 u to the 3/2 plus c. And now I can plug that back in for u. And there you go, the antiderivative for this. Yeah, not at all obvious. Probably if I was playing around with this, I would have probably first split this up, the fraction, up over both of these and canceled out, and maybe tried to do something there. Not an easy integral, but you can break that off and get the derivative of the inside function on the outside. Okay? Again, I'm making that look easy. These are not as easy as I'm making them look. You got to play around, use a lot of scratch paper. The more you do, you get the hang of. Okay, so let me do one more that's kind of tricky like that. Okay, very not clear what to do, but one thing that you can do here is I can factor out a 1 over square root of x, and if I do that, it would be like this. So in other words, if I multiplied the numerator and denominator, this would distribute over both of these, and then you would get the 2x minus square root of x. Okay, so, and the reason, of course, for doing that is that if I let my u equal 2 square root of x minus 1, then the derivative of this is 1 over the square root of x. And in fact, du, I would bring the 1/2 down, and that would cancel that out, and you would just have subtract 1, and you would have you would actually have x to the negative 1/2, which would be exactly what you have here. So when I take the derivative, I get this, and that actually substitutes in perfectly there. And then in for all of this, I can put in the u. So I get 3 over u, and then this is a perfect substitution, like that. And then if I pulled out the 3, then I get something I recognize. 1 over u with respect to u is the natural log of the absolute value of u. So I get 3 natural log of the absolute value of u plus c. And so then I can plug this back in. So 3 times the natural log of 2 square root of x minus 1 plus c. There you go. So there's some other techniques, some kind of more tricky substitution problems. The more you get using it, the better you get at it. And this, it's just a really nice technique of substituting things in and getting an integral that you can then integrate.